In the last class, we introduced iterated cipher. Also, we discuss SPN, substitution permutation network. So as the name says, it uses substitution and permutation both. So in the first round, this is your plain text, and this K1 is first round key that is generated from the given key. K is your symmetric key, and from that K, using some key scheduling algorithm, the round keys K1, K2, etc. Kr are generated. R round block cipher, R round iterated cipher. So these KIs are generated using some key scheduling algorithm. That key scheduling algorithm also we have discussed for SPN. And initially it is your plain text. So whatever, if it is having L bit, then your first round key, the key should also be L bit. So in the specification of SPN, we have taken this plain text to be LM bit string. So your key, round key will also be LM bit string. So they are XORed first. So it produces LM bit string. And then it passes through permutation, it passes through the substitution box, X box. In short, we write it as S box. You get again this LM bit string. Okay, so instead of L bit, I am taking LM bit. Okay, for that example. And then this is the positions are shuffled using the permutation by B. So it produces whatever that is essentially your X1. That is now go through the second round. Same functionality, but it uses the second round key K2. This is also LM bit. If X1 is LM bit string, it is also LM bit string. So it is XOR, then substitution box, it passes to substitution box, resulting string, we permute, shuffle, X2. So in this way, R rounds. This way it continues till R rounds. The final output is your answer, the ciphertext. Okay, so this specification is given here. This is one example of SPN where your substitution box is L bit to L bit. In this example, we have taken L to be 4. So 4-bit string substituted to 4-bit string. So how many 4-bit binary strings are possible? Total 16. So those 16 binary strings, we encode them in hexadecimal. So 0 to 9, then A to F. Okay, and permutation, this is LM bit to LM bit. Permutation is LM bit to LM bit. LM is 16. So this L is 4-bit to 4-bit permutation. Essentially, this your plain text, cipher text, both are LM bit, that is 16-bit. And how it is divided? This 16-bit plain text, this is your X, 16-bit plain text is divided into 4-bit, 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 4-bit. Key is also the key scheduling algorithm. Using the key scheduling algorithm, you generate the, your key is essentially 32-bit string. So your specification is here for this SPN. Your key is, initial key is 32-bit string. By key scheduling algorithm, you produce this R plus 1 many, that means 5 round keys. There are 5 round keys. Each round key is 16-bit. And how we generate this? This is simply shifting. Means first, starting from K1 up to consecutive 16 bits, that is your K1 round key 1. Second round key is from K5. Starting from K5, takes 16 consecutive bits as your 16 consecutive bits in this string K. That is your K2, like that. And the last one, K5, is from 17th position, K17 to K32. That's 16-bit you take. Okay. So this is your key scheduling algorithm for SPN. And for this particular case, L equal to M equal to R equal to 4, your plain text is essentially 16-bit. That 16-bit is XORed. First, it is XORed with the first round key. It is XORed with the first round key. So this is 16-bit XORed with first round key, and then it is passes through. It is passed through the substitution box. Now your substitution box is 4 bits, 4 bit to 4 bit. As I say, substitution box is L bit to L bit, 4 bit to 4 bit. So this is this 4 bit, any 4 bit string here corresponds to encoded as an element in hexadecimal. It is encoded in hexadecimal. So this 4 bit string is essentially corresponding to another 4 bit string. So one hexadecimal place, another hexadecimal. So it is given this pi s is given here. So your encoding of these strings, 4 bit strings are 0, 1 to 9, then 8 to 8, total 16 here. And the permutation, the substitution box, substitution is 0 is substituted as E, 1 is substituted as 4, 2 is substituted as D, like that. So this specification is given for SPN. And permutation also is given. Your permutation for SPN for this particular case is taken to be this. Okay, so the entire thing is, I have this table. I will show it later. So this 16-bit plain text XORed with first round key, it passes through the S box. S box essentially takes you from L bit to L bit. L bit is essentially one hexadecimal encoded as one hexadecimal element. So if it is suppose if this binary representation corresponds to the hexadecimal say A, then it is substituted as 6, like that. Okay, so whatever binary string you get here, you convert it into hexadecimal, and now utilizing this box, wherever it is taking you, that is essentially the output. Okay, so in the substitution box, you get from 4 bit to another 4 bit. So you get hexadecimal, and corresponding 4 bit you represent it in the corresponding 4 bit. Okay, so then again you shuffle according to the permutation pi p. So in this we have the positions 1, 2, 3, 4 positions. So this 4 position, one position is going to one position, second position is going to the 5th position, third position is going to the 9th position, fourth position is going to somewhere. So the specification is given. First position is going to the first position here, second position is here, 5th position, third position is going 9th position, and this fourth position is going somewhere here below this. Okay, so this thing we repeat again with the round key K2, so it passes through the substitution box, shuffle, then it is XORed with K3, round key K3, passes through the S box, shuffle, and then it is XORed with K4, passes through the substitution box. Now in this step, in this fourth step, no shuffling is used at this last step. Okay, so whatever substitution box gives you using substitution cipher, whatever you get here, it is directly XORed with K5, resulting value is your cipher text. Okay, so this is your SPN. Okay, and substitution box, essentially there are total 16-bit plain text, and your key is also 16-bit. The substitution box, we are taking it as 4 bit to 4 bit. So every 4 bit, this whole 16-bit is divided into 4 bit, and this 4 bit is passes through S box. So 4 bit, because this we encode as hexadecimal. So whatever binary string you get here, you convert it into hexadecimal, and then the substitution, whatever substitution you get, it is essentially given in this table. So this binary representation of this hexadecimal taking you to this hexadecimal element. So you have to take as output the hexadecimal. So hexadecimal of this 4. So this hexadecimal, this binary representation of hexadecimal 4. So this way we encode this S box. So SPN, these permutations, I have these permutations. Let me show you this example. I have this. Okay. So here, this specific example I have taken. So your substitution box is this. Okay, some values I have written there. This is the whole substitution box. 0 is substituted as E, 1 is substituted as 4. So this is essentially your encoding into hexadecimal. So 16 total 4-bit strings. We have total 16 4-bit strings. 4-bit 0000. So 4-bit string 16, and we encode it as hexadecimal. So this 0000 corresponds to 0, 0001 corresponds to 1. This one corresponds to 9. So this correspondence you can easily make. Okay, so it is written in this, and that substitution we take 0 is substituted as E, 1 substituted as 4, 2 substituted as D, like that. This is the whole table. And permutation is over the 16 bit. Permutation is over the 16 bit. So 1 to 16, and I am getting a permutation of that 1 to 16 elements here. So you can see 1 position is going to 1 position, 2 is 5th position, 3 9th position, 4 13th position. Now 5th position, this is essentially second S box. So these 4 inputs are going to the second S box. So the same S box, but this 4 bit. Okay, so 4 positions. So first position is 5th position in the second part. It is going to the second position. 6th position remains in the same. 7th position going to 10. 8th position going to 14. Similarly, this is for the third S box shown in the figure. So this is 11. The third position. This is third box, so third position remains same. This is fourth box, so fourth position remains same. So like that. Okay. So this is the SPN. Now another iterated cipher or around block cipher, that is the DES, data encryption standard. Okay, DES. So it actually uses the Feastel structure. What is Feastel structure? So in this DES, there are several specifications. We are going to take this specification. DES, this plain text have a 64-bit plain text. Key is 56 bits, and ciphertext is 64 bits. Plain text and ciphertext are 64 bits. The key is 56 bits. Okay, so this uses this Feastel structure, Feastel cipher. So this is one round of DES. How it operates? So your initially your plain text is 64 bits. So we divide it into 2 parts. Okay, left part L0 R0. Initially it is X0. X0 is 64-bit binary string. So we divide into half, left half and right half. And then in the next iteration, we use the first round key K1 suppose. So in the next iteration, L1 and R1 we generate in this way. So L1 is essentially Ri minus 1. L1 is essentially R0. The right side of the given plain text is your L1, and the right side and R1 will be L0 XORed with F of R0 K1. Okay, so this is your plain text. So initially, what we do, we do not directly use the plain text. We apply an initial permutation. So applying initial permutation on the plain text, this 64-bit we get another 64-bit, a shuffling we are giving. So we divide it into 2 parts, left part 32-bit, right part 32-bit. Okay, and then in DES is this specification is having 16 iterations or rounds, and for each round I from 1 to 16, as the figure says, Li is Ri minus 1, Li is Ri minus 1, and Ri, the right side of the new one is Ri is Li minus 1. Li minus 1 XOR F of Ri minus 1 Ki. So this function is Li minus Ri minus 1, Li minus 1, these are each 32-bit strings. So F function, its output should be 32-bit, otherwise this XOR will not be defined. Okay? So this F function will give you 32-bit output, taking 32-bit two inputs, one is 32-bit and another is 48 bits. So key scheduling algorithm, your key is 56 bits, but your round keys are 48 bits. Round keys are 48 bits. Okay, so this K1, K2, K16, these are generated using key scheduling algorithm. I am going to discuss how these keys are generated. Okay, using the key scheduling algorithm for DES, we are going to discuss this. So each of these keys, round keys, are 48 bits, and those are derived from the given 56-bit key. Okay. So initial permutation, you get L0 R0. This is your L0 R0. Now L1 is simply R0. R1, when you generate this right hand side of Li Ri, so R1 will be Li minus 1 L0 plus XOR F of Ri minus 1 Ki, R0 K1. Okay, so we have to specify this initial permutation. Also, we have to discuss this, how these keys, 48-bit keys, round keys are generated from the given 56-bit key. Also, I have to specify this function f that takes as input 32-bit string as well as a 48-bit round key and gives you a 32-bit string. So these specifications I have to give, and this structure is called Feastel cipher. This type of structures are used in designing symmetric key encryption schemes. DS uses this structure, Feastel type structure. And finally, this is 16 round or 16 iteration. So ultimately you get your ciphertext will be R16, L16. You generate in this way. L0, R0 is your initial plain text. Then you generate L1, R1, L2, R2, L16, R16. And your ciphertext is simply inverse permutation applied on R16, L16. So now you can see this specification of how this function is defined for DES. We are going to discuss that, but before that, let me explain that this function is invertible, easily invertible. While you fix this round key. So this specification is this is needed. This function should be such that it is invertible while you fix your round key. So Feastel type round function is always invertible given the round key. Why? Because if given this Li and Ri, you have to get Ri minus 1, Li minus 1. Okay, so this is from Li minus 1, Ri minus 1, you obtain Li Ri. So invertible means given Li Ri, you have to find Li minus 1, Ri minus 1, provided Ki is known. So this function should be invertible in that sense. This is very easily observed. You can see that Ri minus 1 is essentially Li. If you know that you have your Li Ri. You have Li Ri at your hand. So Ri minus 1 is Li. And Li minus 1 is essentially Ri. If you XOR with Ri, f of this Ri minus 1 is essentially Li. Li you already have. So this Li minus 1 you can recover from this string. Li minus 1 is Ri. Ri you already know. XOR f of Ri minus 1 is essentially Li. Li already you know, comma Ki. So if you know Ki, you can always recover Li minus 1 Ri minus 1 from Li Ri. This is easily invertible function. Now how to construct this function f. So it will output 32-bit. It takes two inputs A and J. Suppose A is 32-bit, J is 48-bit. So here this takes 32-bit string Ri minus 1 and 48-bit key. So here also this for general. Suppose it takes 32-bit input A, 48-bit input J, and it should output 32 bits. For this function, for this DS, it is constructed in this way. So your function is designed in this way. So takes as input A and J. This is 32-bit, this is 48-bit. Now this A is expanded. This is some expansion function. So if you apply E, the expansion function E on A, this is essentially a permuted A with 16 bits appearing twice. This E, when you apply E on A, this is essentially a shuffling of A with extra some bits appearing twice. So the 32 bits now becomes 48 bits. I have this C function this permutation E is this function, this one. Okay, so you can see that it is 1 2 3 4 5 is 32 1 2 3 4 5. Then this 4 5 repeats 4 5 6 7 8 9. Then 8 9 repeats. So this first column and the second column, these are the repetitions. This first column and third column are repetitions. Okay, so here 1 2 3 4 5 6 7 8 9 10 11 12 13 14 like that, 30 31 32 1. So 32 1 appears twice, 4 5 appears twice, 8 9 appears twice. So you can see that essentially this is 1 2 3 4 5 6 1 2 3 4 5 6 7 8. So 48. So repeating this first column and second column means repeating this first column elements and second column elements. These are essentially repetitions. Okay, so so we are repeating essentially 1 2 3 4 5 6 7 8 16 bits. So it gets expanded. The 32-bit expansion function, it adds 16 repeated bits. So you are getting 48 bit. Now you can XOR this 48-bit J and 48-bit expanded A. XOR them. So when you XOR them, you get 48-bit. 48-bit. Now this 48-bit is divided into 8 blocks, each having 6 bits. This is so 48-bit and this is having 8 blocks. So 48 bits, and each BI is 6 bits. Each BI is 6 bits. And this 6 bits goes through box S, substitution box S1. This 6 bits goes through substitution box S2. This is S3. 6 bits are going through this. So this 6 bits, after passing through the substitution box, it produces 4 bit. So this is 6-bit string passing through the substitution box, and it produces 4-bit string. So essentially, after this 48 bits, after passing through the S box, it becomes 32 bit. 32 bit. Because how many? 8 many, and 8 many inputs in each of this box. Input is 6 bits. That means input is 48 bits total, but the output is 4 bits. So so 32 bit here. You are getting 32 bit. So each CI is 32 bit. 8 blocks. Each block in these CIs are 4 bits. Now how these are generated? So these S boxes are also given. Expansion function, as I said, expansion function already I have shown. S boxes also given, and the specifications also given, and how it produces from 6-bit input, it produces 4-bit. It operates in this way. So suppose this 6 bits for BI, for BJ, it is 6 bit string. So suppose it is B1, B2, B3, B4, B5, B6. So this S box are essentially 4 cross 16 array. In this S box, each of these S box is a 4 cross 16 array, 4 rows and 16 columns, and 4 rows and each row having the entry 0 to 15. So there are 16 columns. So each row, first row having entry 0 to 15 in some order, second row also having 0 to 15 in some order, like that. Okay, so all the 4 rows having entries 0 to 15, 0 to 15. So I have one example here. So this is S box 1. So S box 1, so we have rows numbered as 0, 1, 2, 3, 4 rows I have, and 16 columns I have. It is also numbered from 0 to 15. So the first row, essentially one permutation of the elements 0 to 15. This total 16 elements. This is the element. This is the permutation of 0 to 15. So second row also permutation of 0 to 15. So same as this, same like this. Now, if your this BJ is having some B5, suppose B5 is having the 6 bits are B1, B2, B3, B4, B5, B6, then this B1, B6 binary representation, so its integer value gives you the column number, and B2, B3, B4, B5, this is the binary representation. So you convert it into integer. So integer, that is the row number. You can see that in the S box, the rows are numbered from 0 to 15. So so this binary representation, how many bits you need? 4 bits you need. 4 bits you need. So rows can be each row number can be encoded as a column number. Each column number can be encoded as a 4-bit string, and you have 4 rows. So it can be encoded by 2-bit string. So this is suppose 00, 01, 10, 11, and if it is you have 16 digits here, so it corresponds to 0000. This corresponds to 0001, 4-bit string. So to encode these column numbers, you need 4 bits, and to encode these row numbers, you have only 4 rows. So 2 bits sufficient. So if suppose your B is having 6 bits are B1, B2, B3, B4, B5, B6, and B1, B6. Suppose B1, B6 is binary representation. When you take convert it into integer, it is 2, suppose. And B2, B3, B4, B5, this is suppose 4. So this will give you the entry 2, 4. It means column 2 and row 4. So 4 to 8 element. This is column. This is column. This is row. So 2, 4 element. So 2, 4th element. So it will use this substitution 13. And 13 corresponding binary representation. So from 6 bit, you identify this your first bit and second bit corresponds to which row, and the middle 4 bit corresponds to which column. You identify, and that cell value you consider. The binary representation of those, that is essentially your 4-bit output. S box output is 4 bits. So S box outputs this 13 bits. And since each row entries in this whole box are elements of only 0 to 15, each of these elements inside this box all are representable by 4-bit string. Okay, so input B is having 6 bits. B essentially consists of 6 bits, Bj suppose, and when it passes to S box Sj, it produces 4-bit string in this way. So this is the algorithm that is followed. Okay, so this Bj, this is 6 bit. When it passes to Sj, it produces 4 bit in this way. Okay, so you get from 48 bit, you shrink it to 32 bit in this way using the substitution box, and this 32 bit is permuted using a permutation. box. It passes through a permutation box, and finally that is essentially your 32-bit output. Okay, so this permutation box is also specified here. This permutation is used. These specifications are all given for DES design. Okay. Okay, this permutation box is used. So DES F function, crystal cipher F function for DES is designed in this way. So 32-bit A and 48-bit J. These are the inputs of F, and it produces 32-bit in this way. So first 32-bit again, once again, let us go through this F construction. 32-bit A first expanded to 48-bit. Expansion already I have mentioned. Some it is essentially A is permuted, and not only permuted, some bits are repeated. 16 bits are repeated, so it becomes 48-bit. Now this 48-bit permuted A and permuted and as well as expanded A is XORed with 48-bit J. And so we get 48-bit. Now from 48-bit you have to shrink it to 32-bit. How? You shrink it to 32-bit by passing them through the S box. So this whole 48-bit is divided into 8 blocks, each block having 6 bits. Each 6 bit is passes through S box. Each S boxes are essentially 4x16 arrays, where the entries inside this S box are elements from 0 to 15. So each each entry in S box can be encoded as a 4-bit string. And the column numbers also can be encoded as 4-bit string. Rows can be encoded as 2-bit string. So if from this B box, it is 6 bits. So first bit and last bit corresponds to which row you can identify, and for this B1 and B6 corresponds to row, and B2, B3, B4, B5 corresponds to column. That position RCH entry in the S box you pick, and binary representation of that is essentially your output of S box. Okay, so essentially from 48-bit you can shrink it to 32-bit, and finally we apply a permutation, shuffle it, and get the output. Shuffling that permutation is given. This expansion matrix is also given. Okay, so one S box I have shown, and the other S box also I have that. Let me show. So these are the permutation tables. Let me just make it a little bit bigger. Okay, so initial permutation, I have not specified initial permutation. Initial permutation is written in this way. So in the crystal cipher, given plain text, you don't use that plain text directly. You apply a permutation on that. This permutation is given here. And from that permutation, you can easily find the inverse permutation. So this is your permutation. This is your inverse permutation, and expansion permutation already I have discussed this expansion permutation, and the permutation function. These two essentially I have mentioned. Okay. And S box. This is key scheduling algorithm. I yet to discuss. I have to discuss key scheduling algorithm. I will come to that later. These are the S box. First S box I have in my notes. I have this first S box. The other S boxes are like this. Okay, so these S boxes are fixed for this DES design. Okay, so the designers, they already gave these S boxes. And another thing is, okay. So key scheduling algorithm I have to, so only thing remains is key scheduling algorithm. Let me do it. 65. Okay. So in DES we have discussed the design. This F function, how it gives you 32-bit string, where it essentially takes a 32-bit input, another argument 48-bit. Okay, so this also I have discussed. Only thing, this IP also I have discussed. Only thing that is yet to be discussed is this key scheduling algorithm. So your key is 56 bits, 56 bits key, and from this 56 bits key, you have to generate round keys. K1, K2, K16. Total 16 rounds we have for various. So this 16 round keys, each are 48-bit strings. Each are 48-bit strings. Now, how to get that? It is not like SPN. The SPN, we have specified the key, how to generate this key. So this algorithm, this key scheduling algorithm varies from design to design. For DS, it is, let me discuss this. So as I said earlier, that DES uses the rotor principle. Okay, some rotation is used. So this essentially, so let me illustrate this. So this is your picture. Whether it is visible or not. No. Okay, so this is the details of one round DES. This part already I have discussed. So Li minus 1, Ri minus 1, 32-bit, 32-bit. Li minus 1, Ri minus, Li is essentially Ri minus 1. But Ri, how to get Ri? So you XOR Li minus 1 with this. Okay. So Ri minus 1, this is your f function. This f function takes Ri. This f function already I have specified how this f function works. This f function takes Ri minus 1 and the round key Ki as its input. So Ki is 48-bit and Ri minus 1 is 32-bit. So it calculates f at Ri minus 1 Ki and produces whatever it produces, that is XORed with Li minus 1. That is this is your crystal structure. Now how to generate the key? So these keys are generated using left shift, circular left shift. That is essentially the rotor principle. So initially you have your initial key. That initial key is 56-bit. 56-bit key. From 56-bit key you have to generate 48-bit round key. So for 56-bit key, you divide it into initially your 56-bit key. You apply a permutation. Apply a permutation, and whatever you get, that is also 56-bit, and you divide it into two parts, 28-bit, 28-bit. Okay, so each this 28-bit you give a left circular shift. So left circular shift means left circular shift means everything is the whole string is shifted in 28-bit strings shifted left, and circular, the first element comes as the last element. So left shift, we are giving left shift. Now how many left shift? Generally 1 or 2 left shifts are given for this part as well as for this part, and it depends on in which round you are in. So in first round, so we have that table also, the specifications also, how many shifts you are going to use. So this is generally 1 or 2 shifts we take left circular shift. So your initial key, you shuffle it using a permutation. So 56-bit key, shuffle it, you get 56-bit, you divide it into 28-bit, 28-bit. 28-bit left part, you give a left shift here, 1 or 2 left shift, circular left shift. In the right part also, same thing you do. Same number of left shift or right shift you give. And then so this part, this left shift part and right shift part, whatever combined you get, essentially it is again 56-bit. Generally, just you have given a shift. So it is not shrink, it is still 56 bit. So this is 28, 28 is 56 bits. Now you have to shrink it to 48 bit. How? We take we shuffle them and discard some elements from them. Okay, so how to discard those? Those are specified. Those are specified. You say this they call a permuted choice 2. They have taken a permuted choice 2. A permuted choice 1 they are using for shuffling the initial key. As I said, initial key we first shuffle it using this permutation choice 1, and then you divide it into two parts: left shift, circular shift, one or two left shift, left circular shift, and in this part also one or two left circular shift. You give, and this 56 bit whatever you get, you have to shuffle them again using this another permutation choice. This is not exactly permutation, some bits we discard here. Okay, you get 48 bit. Okay, so your key this one is left part is now after circular shape, left part is become Ci. Initially it was Ci minus 1 suppose, and right part is becoming Di. Okay, so this is essentially key scheduling. This is rotor principle is used, rotation is used. We are giving a rotation. This whole thing is shifted left once or twice depending on your round, in which round you are in. I have these X boxes already I have discussed. Input key, here I have discussed these permutations. Let me make it a little bigger font. So here your input key, so this is this input key, this is 56 bit, your input key is 56 bit. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 56 bit. This column is just checksum. The parity, it checks the parity. Checksum, it is checksum. Okay, so this is your input key. Input key, and this permutation choice. So initially your key was 56 bit key. The 8th position is check bit, check position. Then 9, 10, 11, 12, 15, 16 position is again check position. Okay, so key is read in this way. This is check position. 17, 18, 25, 23, then 24 check position, like that. So although we are writing this the 64 bit, your key is essentially this part. This is check bits. Okay, so this part, this is 56 bit key. Now you shuffle them using this permuted choice. So this 56 bit, you get another 56 bit according to the shuffling. Okay, this specification is given. So initial key, you apply this permutation and you divide it into two parts, 28 bit and 28 bit. So on this 28 bit, each of this 28 bit, you give left shift in each of these 28 bits. So in the first round, how many shifts you are going to use, that is given in this table. So you have total 16 rounds. So in the first row, this is essentially number of rounds, round number 1, 2, 3, 4 up to 16. And how many shifts are allowed for the first round? 1 shift. For circular left shift, for the second round also 1, for the third round 2, fourth round 2, it is specified. Okay, it is specified. And after giving left 28 bit left shift and right 28 bits left shift, circular shift, whatever you get, you get again 58 bit string, and you have to shrink it into 48 bit in this using this permuted choice 2, second permutation. Some bits are discarded according to this specification. So shuffling is essentially after giving this round, giving this shifting, left shifting, your first position means first position is going 14 position is coming here. So that in the shuffling thing, 58-bit shuffling thing, 14 position coming to the first position, 17 position is coming to the second position, like that. Okay, so this permutation is given, and you can see that this is essentially how many rows you have: 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6, 7, 8. So 48. So you get 48. Here in PC1 or input key, these are 56-bit, but this second permutation is discarding some specific digits, specific positions, some specific bits it is discarding. Okay, according to this. Say I have one second position is discarded. 3, 4. The second position is there. Some positions we are discarding. Okay. So from this 48, so some positions are discarded. So this specification is given. Okay. So more or less I have completed DES. Okay. So DES, SPN we have discussed, and DES it uses the rotor principle also we have discussed, and so we have discussed. Okay, and the next thing is I'm going to stop here. So before discussing stream cipher, we have to introduce some more block ciphers. Triple DES, also DES, what are the attacks? DES is not secure, what are the attacks? Those things will be discussed, and what is triple DES, how it works, and finally AES was proposed. AES or the ring-wheel, it was proposed as an alternative of DES. So those designs will be discussed. Okay, after that I will come to this stream cipher, and those AES, triple DES, those will be taught by Professor Saurabh Mukhopadhyay. Okay, for few classes, coming few classes, he will be teaching you those. Let us stop here.